Hi, Matthew. Welcome. Thanks for doing this. So today we are going to talk about generative AI for code. You are the CEO of Diffblue, a very interesting startup based in the UK, originally a spin-off from Oxford University. And amongst other accolades, you were recently named to the CB Insights AI 100 list, so the most promising artificial intelligence startups of 2023. And of course, you're listed on the annual Mad Landscape that we produce here every year at First Mark. So I'd love to take it from the top and maybe have you paint a broad picture, if you will, of the generative AI for code space, which is something that people have been very excited about, and there seems to be a lot of players doing different things. So it'd be really interesting to sort of like understand who does what and the different approaches, and then go into what Diffblue does specifically.
Yeah, sounds great. So thanks for having me on the podcast. So if we think about generative AI, everyone's heard of ChatGPT and Copilot for the most part, which are large language model based approaches. And essentially today you see two different technological approaches. One is based on language models, and the other one is based on reinforcement learning. Tab9 was probably one of the earliest startups in this space. So they built language models. They used some of the earlier open source OpenAI models and GPT back when OpenAI used to open source things. And they've taken those and essentially evolved them over time, and sort of they have their own proprietary model at this point. So similar in architecture in a sense to Copilot, where those tools essentially, they have a prompt that's based on what's in the IDE, the code that's behind the insertion point, so what's sort of come before that point and what comes after. And what you're asking the model to do is predict what comes in between. And so it uses information from, maybe you've got a comment about what you want this code to do, or there's some half-written function or something like that, and it's going to try and figure out what it needs to do to fill in. And so those models fundamentally are trained on lots and lots of code examples, and so they learn statistical text patterns for code, and they've been trained in lots of different languages, which is how they're able to generalize across languages. And so these tools essentially make, they're like autocomplete on steroids. If you think about autocomplete's obviously been around for decades, but what they've done is essentially make that much more powerful. And that's where a lot of the appeal comes from. It's an approach that developers are already familiar with. They already know about autocomplete. There's just better autocomplete. It can do more. And so it's very easy for developers to pick these tools up and start using them. And the code is by and large not correct. If you look at some of Microsoft's own statistics for Copilot about sort of acceptance rates by developers, they've done some work looking at exactly how many suggestions out of Copilot are taken by developer, how ones are rejected. Then you can see sort of the acceptance rate varies depending on the seniority of the programmer. So more senior programmers are more discerning, they reject more completions. Junior developers tend to take more. But in general, it sort of hovers around, depending on the language, the context, somewhere around the 50% mark. And a lot of it depends on the kind of code that you're writing. So essentially what is happening here is that you get fantastic generality from this, and the generality enables, it comes with errors. I mean, essentially that's the trade-off you're making. The large language model is not going to be completely correct, but it might get you started, and a developer can sort of take it to completion, make it work, turn it into something useful. The approach with reinforcement learning is quite different in that there's no pre-training in reinforcement learning. So the idea with reinforcement learning is that you want to conduct a search of some kind to go find what you're looking for. You're trying to find a solution as opposed to make a prediction. So it's been used perhaps most famously for game playing. So if you think about things like Google AlphaGo, is based on reinforcement learning, where you're searching for the best Go move. Yep. Now, in the case of Go, the reason you have to do this at all in the first place is because the possible number of moves in Go is so large. Right, so the search strategy is only useful when your search space is too big for you to look at all of the alternatives. That's also why you don't see AI for playing chess, because chess search space is small enough. You can just look at all the possible moves, just try them all and pick the best one. And you can't do that for Go. So essentially what reinforcement learning does is that you have some kind of prediction for what a good solution is. So the idea of reinforcement learning fundamentally is you can't look at all the solutions. So what you do is you spend a lot more time looking in places where solutions are most likely to be found. So you need some way of figuring out what that most likely space is. In the case of Go, then AlphaGo looks at a move tree and sort of makes some predictions about who's going to win the game. And then it just tries different moves. And this is the key of reinforcement learning. The learning happens when you try the different alternatives. You, in the case of Go, you play the move, you look at your prediction about who's going to win, and then you might sort of follow a path of moves and keep following that and see, is your prediction for winning getting better or is it getting worse? And if it's getting worse, you might want to backtrack, try some other moves and sort of further up in the move tree if you think about it that way. And through that process, at the end of that process, you've got the best move that you can find. It's not guaranteed to be the best move, but as we saw with AlphaGo, it's good enough that it can, it's beaten Go masters in some competitions. Essentially, you can use the same for coding. This is what we do at Diffblue, where we're looking for tests. So we're writing unit tests. So unit test isolates a unit
and
software.
We'll talk about in a second what that means. But let's hold that thought for now.
Okay. So essentially, we're searching for the best test. And so in our case, we analyze the program, and that gives us an idea about where the best solutions might be found. So where the tests might be, what they might look like. We write that first test, we run it against the code, we see how it performs, what kind of coverage it gets, does it test boundary conditions, how much branch coverage do we have, things like that. That enables us to improve our prediction about what a good test would be. We make that prediction, we build the test, we run it, we try it, and we iterate through that loop. And at the end of that process, we have found the best test that we can for a particular block of code. Google DeepMind has also applied this approach to things like code optimization, where essentially they're searching for more efficient implementations of a particular algorithm. So they shaved about 7% off the sort algorithm in the C++ library, which doesn't sound like a lot, but considering how often that code is called, that's actually quite a big win.
Yep. Okay. And so are you 100% focused on reinforcement learning, or is that a combination of reinforcement learning and LLMs, or is that people? I'm sure I've heard of GPT being having a sort of reinforcement learning from human feedback, or LHF being a part of what they do overall. So is that a hybrid approach, or is that a solely reinforcement learning?
Yeah, we use an ensemble approach. So we've got different aspects of the models, and we've obviously been playing with large language models to see if we can improve on that process. So some of this is like, how do you make predictions? And you can use large language models to do some of that work. You can have them make some predictions for you about what might a good test look like and so on. So we do use a number of different techniques. It's not purely all about reinforcement learning, but the big difference is that in large language models, essentially the reinforcement learning is used to tune the model and have it prefer some responses over others. And so part of what you're doing is correcting for the randomness that's in a large language model and teaching it to prefer some outcomes over others, which is, and fundamentally what we're doing with reinforcement learning was reinforcement learning first and foremost, how you guide the algorithm, how you assess the effectiveness of what we're doing, how we make predictions. That is ensemble, but the emphasis is different, right? It's primarily about reinforcement learning as opposed to using reinforcement learning to correct what a large language model has produced.
Okay, great. So I interrupted you a minute ago. That unit tests, before we go further into like how things work, let's backtrack a bit and talk about what that is. So to make it interesting to a broad audience that may not be familiar with the intricacies of this. So what is a unit, I guess, and what is unit test, and why did you all pick that area compared to like other areas of code generation?
Yes. So the idea with unit tests is you isolate one module of the software and you test everything inside of that in isolation. So unit tests have been around for about 25 years as a concept, and you can think of it if we make a simple analogy about production line for a car, right? When you're making a car, you check that the brakes work when you put them on the car. You don't wait until the test drive at the end of the production line to find out if the brakes work. And so the same idea in software is called shift left. Now that's a crude analogy, but it works. It gives you the right idea. You're essentially trying to make it so that you find defects as soon as possible. And so the idea with unit tests is that a developer can run them, and they run quickly, and they run them at the time they're writing the code, so that failures in unit tests can very quickly be fixed by the developer, because they're in the headspace of that code. They've got, they know exactly what they're doing. They've probably been working on this for a while. Everything is ready, there for them to be able to make a change to the code and fix an issue that they find. And that's one fewer defect that then shows up in QA, because fixing bugs that are found in QA takes much, much longer. The idea of,
I guess typically, just to again, like make this super basic for a broad group of people. So typically, the developers would not test, and they would just like write code, and then this would go into a separate group of people who'd actually test. And the idea is that the developers should be testing in a way that they were not originally. Is that part of the idea, or is that too much of a caricature?
It's a simplification, but it's pretty much what happens. I mean, so when a developer is working on something, they will test it themselves. The question is how they might do that. They might just test if their piece works. They might build the entire application, and maybe if they're making a change to how the interface works, they go in and make sure that when they do the things in the interface, do the right things happen. And so part of the challenge with that is that, one, you need to build the entire application, and to run it, you might need dependencies that are like a database or something like that. So that can end up being quite slow. And so what developers try to do is they don't really want to have to deal with that, so they try and simplify things for themselves and get enough confidence. So it's not like developers are reckless, but there are changes that they're putting in, plus the changes that other people are putting in, and then sometimes the software doesn't build it, and it's the works on my machine problem, right?
Okay. And so historically, before Diffblue, over the last 25 years, like how did people do it?
Yeah, so historically what they did is they spent a lot of time in quality assurance. So there was a separate QA team whose job it was to look at the original, what's the software supposed to do, the original specification, and take that idea and check that the software does what it's supposed to.
And what kind of tools do they use to do that?
So it depends what kind of software you're building. But let's say if you're building a web application or a mobile application, a lot of it is clicking on buttons and making sure the right thing happens. So working through the interface is typically how they would do that. And in the sort of bad old days, that was all done manually. So people literally sitting in front of screens clicking on buttons. Now, and obviously everyone wants to automate that, and there's a vast number of products out there to automate UI testing these days. And web servers, web applications and browsers has made that easier to automate. And so you can automate the manual process out of this. The fundamental issue, though, is still that all when the software doesn't work is that it doesn't work. You don't know why. So the next thing has to happen is the triage of okay, it does the wrong thing. Why is it doing the wrong thing? And sort of working backwards from that problem to what's the root cause. That by itself might take days or weeks of work, depending on how complex things are. And especially in complex systems where you've got databases, you've got caches, you've got all these other things happening all at the same time, you get into these problems that are hard to reproduce because they only happen when you've got certain combination of things all happening at the same time. And that makes fixing those bugs very time consuming. So just root causing it can be very difficult. And then the developer has probably moved on to working on something else. They have to stop what they're doing, go back to that code that they were working on maybe a month ago, try and figure out what's going on, try and figure out what the problem is to fix for it. And then they have to send it back to QA to make sure, do we really fix that? So that process is just much longer, much more time consuming for everyone.
Okay.
But that's what people did.
Yeah. All right. And so now with Diffblue and reinforcement learning, then how does that work?
So the challenge for a lot of organizations, and this is sort of how Diffblue got founded, your question earlier on about that, is that unit testing is tedious, error-prone stuff to do. It can be quite difficult code to write. And the idea because you have to test a single unit, you have to figure out how to isolate just that unit. And so for a database-driven application, where you're expecting to have a database on the back end, you don't want to have to do that anymore. So you're going to have to figure out how to essentially emulate the database. And so you're looking at trying to synthesize test data or synthesize dummy data, pretend to get the same thing back from the database that you would get, and that's called mocking. So that process itself is very tedious. You have to get exactly the right configuration. You have to use a mocking subsystem. You have to learn how to use that. That just by itself can get very complicated and very slow. And this is why developers don't like writing these tests. And fundamentally, they're not paid to write tests. They're paid to deliver the functionality, the new things in the application, the fixes to the application, the updates. And tests are just there as part of the process to help them. But what it means, especially in larger organizations, is that you've got very large applications that run big chunks of the organization. They might have been around 15, 20 years. People that first wrote them are long gone. There's no one person who understands the entire application and how it works. And so that process is now very, very difficult to do, to go back and sort of get unit tests when you didn't have them before, or it's not been the norm to write unit tests. Is very, very difficult. It's like a mountain to climb.
And so so there's the problem of new test of a new code, but of course there's like the whole legacy thing. Okay, all right, fascinating.
Yeah. So legacy is a big challenge. I mean, and depends what you mean by legacy as well. I mean, in a lot of cases, the entire reason that unit tests are useful for an application is because it's very important to the organization.
Okay, that's really helpful. Thanks. So how does Diffblue solve that problem then? Like, what are the actual sort of high-level mechanics of how it works?
Yes. So our product writes this test code fully autonomously, so very different from LLMs. And in order to do that, we use reinforcement learning to help us find those tests. So the basic steps are, the first thing we do is analyze the program. So we see the entire source code of the application. So again, different to LLMs where you've got limited context, you've got before the insertion point, after the insertion point, we've got the entire program. And so we do analysis on that, and that enables us to come up with our first guess, essentially, of our first prediction of what a good test would be. So we take it method by method. So all the functions of the program, so enumerate all of those. You understand exactly the context of each method and how you're supposed to call it and what you're supposed to feed into it, all of those things.
So it's like it's like a mapping exercise of some sort.
Yeah, so you essentially compute what's called a call graph, like all of the functions of the program, how they call each other, what the signatures are, so what data do they need, because you're going to have to create that data to pass it in to test them. And we also look at the structure of the program. We do a little bit of what's called data flow analysis. So we look at how data moves through the program to a certain extent. And that gives us a way for us to produce that first test, and essentially gives us our first set of predictions as to what useful tests might be. And so then we write the first test. So we essentially compile it. run it against the method under test. So we call the code that we're trying to test with our guess at what a good test might look like, with the data that we think might work, and we see how it does. So we evaluate the effectiveness of that. So we look at how much coverage did we get? Did we hit branches? Are these interesting values that would be on the boundaries of changing the behavior of the code? So if there's something in there that says if a value is greater than 100, then do something different. And so you want to maybe feed in like 1 and 100 and 101 and 99 and try and sort of exercise that boundary. And from we want to know, does it throw an exception? And then what does it do? So what in the state of the program changes? Because we're going to need to know that that's our information that we need to write assertions for exactly what that method does. And then we just keep going and we iterate through that process and we repeat that again for every single method in the program. So, we have customers, they have million line Java applications. They might get 50,000 unit tests for a million line Java application. Yeah.
That's incredible. Sounds like incredibly just like complex systems, like an interdependency and all the things. When you run those jobs, is that like super compute intensive? It takes a while, or like what's the right way to think about it?
Well, ironically, it's far less compute intensive than large language models because our stuff will run, will just run on a regular CPU, and so we, for one of the banks, they had an application. We wrote like 3,100 tests in about 8 hours. Now, they estimated that that's like a year's work for a single developer, 3,000 tests.
Wow.
And we can do that in 8 hours. Some of it depends on what the code is, but that sort of gives you the sense of how much time you're saving.
Okay. And currently you support Java, if I read correctly, because that dimension as well, like the tests are very language related.
Yes.
So presumably you chose Java because that's the most widely used for legacy kind of like application kind of code. Is that right? Or
yeah, that's right, and that is why we chose it. So it's been top enterprise programming language for it's been the top 3 for the last 25 years, something like that.
Yep.
So there's vast amounts. Yeah.
Do you have others on the roadmap, or it doesn't even matter because the Java universe is so large?
No, we will do others in the future. So we just added our second language, which is called Kotlin. So Kotlin is also uses Java Virtual Machine. You get a lot of applications that are hybrid Kotlin and Java today. And so it was a good second language for us to do. Some of our customers also have applications that they wanted us to support it. And we'll absolutely do more languages in the future. It's the usual thing with a small company. You got to do one thing incredibly well when you start out.
Yeah. And it is, since we're talking sort of about roadmap, like it feels like, again, like a very complex world and a vast universe of customers you can sign and all the things. Is part of the idea over time to expand into other things like I don't know, code migration? If you can, if you spend a lot of time in the gnarly world of legacy software for large institutions, is part of the idea. Like one, you test them, but like second, it's like, okay, well, this is how you should be writing it, or like porting it to a different language or whatever it is.
Yeah, there's a lot you can do. If you look at what some of the very, very large companies do, like you look at what Meta does. If you're a software developer at Meta and there's a bug in your code, when you open your IDE, you don't just have your code there. You also have a suggestion for a fix. Mm-hmm. And so you can apply the technology, apply the approach that we use to lots of other coding problems where you're trying to find better code, essentially. So there's that kind of thing you can do in the future, and there's all kinds of improvements to existing code as well as writing brand new code.
Yeah. Does that mean that the COBOL situation is going to be fixed in the short term? So, COBOL being that very old language that still runs in production globally at somewhat of a massive scale, especially in financial institutions, as far as I know.
Yeah, so it's funny you mentioned that. We have a number of projects underway where they're doing COBOL to Java migrations, and so part of that is the testing part's very, very important for them to be sure that the Java code is doing what the COBOL code did. And also it gives them ability to then evolve that and refactor that Java code and maintain it over the long term rather than just sort of taking the application, doing a one-time conversion. They want to update the program, right? So that's a big part of it. And interestingly, the motivation for that is the cost of things like microfocus and the software that runs on the mainframe. That's the big driver because PE companies bought all of those software products and raised the price.
Yep. So while we had talking about code in financial institutions, like I read somewhere like a nice quote from Citibank, and like I saw that you guys were exhibiting at various financial services kind of like trade show and conferences. So is that the core target for you all, or how do you think, I guess, about go to market?
Yeah. So we got started in financial services because Goldman Sachs was an early backer. And so a lot of it was word of mouth and working, all those guys talk to each other, people move around. That's how we got started. And so we grew out of that. But, more recently, we've got customers like Cisco and AstraZeneca, and, everyone has the same problem. It's not limited to financial services.
Yep. But you're focused on the enterprise, so large code bases. If I'm a smaller startup, I may have less of that problem, or I'm just too small to be an interesting customer.
No. You may still have the problem.
Okay.
Yes. You may still have the problem, and also what you find is, we sell our go-to-market strategy is very much sort of land and expand. So we might start with a single team. That's exactly how we started at Citi, with a single team, and expanded from there. They've got a problem, but if things go well, other teams learn about it, they find more uses for it, and we can expand.
Okay, and you sell to the CIO, or you sell to the developer, or you sell to the VP Eng? I get you top down, bottom up, the middle.
Yeah, it's a little bit of both. So it's usually somebody like a VP of engineering or senior director of engineering who's the buyer, the economic buyer. Now we have a free community edition. You can just try our product. Very important because most people have never seen anything like what we do before, so they don't know what to expect. So they want to just try it. And then if they like it, then they come back to us at some point later and say we'd like to buy a Teams edition. Get started.
And how do people perceive the fact that it's fully autonomous, like versus again GitHub Copilot, which, as the name indicates, has more of that Copilot kind of interaction mode, where the human may feel like they're more in control. Like this is like autonomous AI. It's like, are people excited by it, spooked out by it? Like how do they react?
Well, we offer both models as well. So, we offer an interactive model where you can just point to your code and say, give me your tests, and we will just give you tests then and there. And so that's, much more like a developer is used to. But they might be doing that in the context of, we previously wrote 20,000 tests. And so they're in test maintenance mode. Like they've written some new code, they need tests for it, or they're maintaining the code, and so the tests are obsolete and they need new ones to replace the old ones, and they can do that interactively. So we've made the product so the most important thing is it works the way the developers are comfortable with working. You can go the fully autonomous route where the developers don't use the tool interactively at all. They just get the test. They're there in the baseline of the code. They can run them. When the tests are obsolete, they can just delete them because we can just regenerate new ones. So that's a very, for some developers, that's a bridge too far. So it's really what people are comfortable with. Yeah.
And I saw when I was prepping for this, looking at the demo that you have on the website, it's still very much transparent, right? It shows you exactly the line where the problem might be. And
yeah, that's right. Yeah. Yeah, and we design the product to fit in with the way people do testing. We use this, JUnit and TestNG are the two sort of open source frameworks for testing in Java. We generate code that uses those. It's what they're used to.
Still in the general vein of how people react to it and humans, obviously the unavoidable question around all things AI and generative AI in particular is AI and jobs. I was alluding to a nice quote from a MD at Citibank, Jonathan Lofthouse, one of your customers, MD and Global Head of Markets Technology at Citibank, sort of making the point that this is not taking anyone's job, right? How do you
That's right.
position the product and experience from that perspective?
Yeah, it's about developer productivity, which is very important to these organizations because software is really critical to how they compete these days. They are large software organizations. And, at Citi, what they wanted to do was reduce cycle times. So how quickly can we ship? How can we increase the frequency at which we ship? And because that will make us more competitive. And also, how do we improve the productivity of our developers so they spend more time on, frankly, the more important parts of their job, which is implementing what we want in software as opposed to having to write all of the tests and doing the drudgery. I mean, the analogy I like to make is it's kind of like the shift 35 years ago from sort of assembly language to compiled languages, right? So what you did as a developer really changed. People used to write code in assembly language back when, computers were far less powerful, they had far less memory. And so, the original versions of BASIC were written by, Bill Gates and Paul Allen and all those guys in assembler. And then higher level languages came along because they offered this massive productivity improvement, right? So what you did as a programmer changed. You were now, instead of writing individual machine level instructions, you were thinking about algorithms and data structures and operating at that level. And that's where that productivity came from. You got this shift in what you spent your time on to higher value things. And it's essentially that all over again. And I think, we talked a little bit about large language models and that approach and how it's an extension of what developers do today, but it also is lower impact for that reason. So code suggestion, you could really still only go as fast as a human can go because a human has to review that, decide whether it's useful or not. If it is useful, fit it into the code and finish the work. You're still basically going at the speed of a human, whereas with fully autonomous code generation, you're much, much faster. Now, it's more of a change to how people work, but the benefit is much higher. And so I think, that is really the promise, or it should be the promise of what machine learning and artificial intelligence should be able to do.
Mm-hmm. Great. Well said. Very interesting. You have just looking around on Twitter and some press and everything. You have some really interesting, spicy takes. I guess this is the term of the day. Spicy takes. And one that caught my attention recently was prompt engineering is not a thing. Do you want to expand on that and explain what that is?
Yeah. Yes. It was. This came out of some reflection about exactly how large language models work and do what they do so well. And fundamentally, and some experiences using very early versions of large language models for code completion, where what we found is that very, very small changes in what you asked the model to do and the code you asked it to write could result in huge differences in what you got, the output that you got. And that's essentially what people are talking about with prompt engineering, because what Copilot is doing is basically doing a lot of behind the scenes, doing a lot of work on the prompt to try and get you the best code for a particular situation. But fundamentally, these models are so big and so complicated that nobody knows what they're going to do. You don't have any predictability. And so the idea that there's something called prompt engineering in the sense of you're applying an approach because it's going to give you the output that you desire, is a complete fallacy. At best, it's trial and error. It's prompt trial and error. And there are rules of thumb about how you construct a good prompt and so on, which is, based on the way that the back-end model works, but it's not engineering. It's not engineering in the traditional sense.
Okay, so I should revise my LinkedIn profile to no longer say engineer. Yeah, all right. And another one I liked, which maybe you alluded to, was, I think that was a tweet. One problem with large language models is their largeness. That's what do you mean by that?
Well, one of the reasons we've been successful in highly regulated industries is because we made our software so that they could run it locally. They could run it in their own development environment, inside their own infrastructure. They don't have to send their code anywhere. They don't have to worry about any of the privacy or IP implications of any of that. And it's incredibly difficult to run large language models locally, and it's incredibly expensive. And so we built a version of our product where we used the large language model to generate all the tests. So we took our reinforcement learning engine out and put in large language model, and we did a lot of work on prompts and so on. And our product will write a test in about a second and a half, and we were getting 40 seconds to write a test with a couple of 100 billion parameter large language model on the back end. And now we could have paid more and probably speeded that up. But those very practical considerations make a difference, make a big difference. And so, practically whether people are going to be able to use the technology, does it solve some of their privacy concerns? The large language model, the largeness of large language models works against you in those situations. It's one of the reasons I think that we're going to see more smaller models. And you've got startups now emerging, which are essentially trying to distill down from a large model into something much smaller that will run without a GPU, and they're trying to automate that process for exactly that reason.
Mm-hmm. Yeah, and I also read somewhere like you're a big fan of open source as well, like smaller models, but also open source. Same reasoning.
Yeah. Yes, same reasoning. But I mean, also what we've seen happen with some of the image generation stuff with diffusion algorithms. So the most successful one of those, based on the stability engine, has a very, very rapid improvement because there's a whole bunch of people tinkering there, and they don't have a lot of money. They don't have 1,000 GPUs to run it on. And so they've made, the combination of all those people working together has led to some very rapid advances. And very quickly, stability, the open source project stability, got to be better than DALL-E 2, and DALL-E 2, spend on DALL-E 2 is immense. So I'm a big fan of open source.
Yep. And you think open source is going to catch up to, that's sort of the question of the day, abundantly on Twitter every other minute, or I should say X, I guess, every other minute. But you think the ultimate win of victory of open source is the writing is on the wall?
I think so. I think because it allows that level of innovation I just talked about, and I think also it gives people the ability to specialize these models to a particular task. The genius of ChatGPT is that it is so general, right? It's a text generation engine that will do anything. It'll write you a poem, it'll write you a story. It can pretend to be Shakespeare. I mean, and that really just catches everyone's imagination, and it suddenly becomes a household thing. And it's brilliant. But if in a commercial context, you don't need it to be all those things all at once. You need it to do one thing incredibly well, which is your problem, whatever your problem is.
Okay. All right. So maybe to close, I'd love to go in a pretty different direction. You are based in the UK. You're a spin-off from Oxford, and for like anybody who watches this online on YouTube as opposed to listening to the podcast, your Zoom background is a famous bridge at Oxford University. Like I'm personally a huge fan of this sort of like Europe to US or Europe to the rest of the world kind of startups. And it seems that the UK, as in particular, has produced a bunch of really interesting company. We're, not to be the VC plugging their companies, but we're investors in Synthesia. You mentioned Stable Diffusion, Stability AI is originally from the UK. You guys obviously are from the UK. I guess what's the reason for that? Why is the UK kind of like AI scene vibrant? What are the things, the parts of it that you're excited about? What parts need more work, and what's your overall take?
Yeah, there's just a huge amount of talent over here. Obviously I'm sitting here in Oxford, but it's not just Oxford and Cambridge. It's like all over the country. There's a lot of research, and as you said, there's a sort of strong history of really good technology coming out of the UK.
I forgot DeepMind in my little list.
I was going to say, I have to say, Demis Hassabis and all of those guys, right? UCL,
yes,
and Oxford together. Sort of that's where DeepMind came from. I mean, what's interesting about DeepMind is one of the reasons that Demis said that one of the reasons that they went over to Google is because they were trying to develop LLMs and they needed access to capital, right? And I think that is a really good marriage between the VC world and what's coming out, and the talent that's here is not necessarily the money in research institutions to take this and take it to places where it can do the most good. And so that's the other important part. And we've been very fortunate to have investors who are, see the potential.
Mm-hmm. What's currently, what do you wish there was in the UK or Europe that would help build, the next OpenAI or next Google out of Europe?
Well, I don't think Brexit has done us any favors. I don't know if that's even a controversial thing to say anymore in the UK, but I think it hurt us. We had Brexit exodus of talent where people just said, you know what, I'm going back to France, or I'm going back to wherever. I think especially the kind of resources you have to apply to this, the war for talent, all those other things, better relations with the rest of Europe and being able to work together more effectively is a good thing.
Yep. Okay, great. All right. Well, it's been wonderful. What's happening next at Diffblue in like the next few months that people should be on the lookout for?
So we have an exciting partnership in the works that I can't talk about now, but we'll be announcing probably in December. We're deepening a relationship with one of our customers, and we'll have more to say about that in the next few months as well.
Okay. Very exciting. Where do people find you online? I mentioned your Twitter. What's your handle? I guess we'll add that in the show notes. But where do people find you and learn more?
Yeah, you find me on Twitter, Mathew Lodge, Mathew with one T. But it's fairly straightforward. And MathewLodge.com, that will give you all the links to all my social media accounts. I'm also on Instagram. I post a lot of photography on Instagram. That's my hobby.
Oh, nice.
I took that picture that's behind me. So,
very good.
So you can find me there at LinkedIn. I'm LinkedIn/in/Mathew. So that's me.
Oh, very, very, very chic. Okay. First time in your LinkedIn handle. All right. Okay. Well, it's been wonderful. Thank you so much. Really appreciate it. And congratulations on everything you have built so far, and look forward to seeing the announcements in the next few weeks and months.
All right. Thank you very much. I appreciate it. And thanks for having me on. Thank you. Bye.